In this problem, I'm looking at a set of 5 different resistors that are hooked up in a little bit more complicated of a circuit. And what I'm trying to find is the current and the voltage that are applied to each of the 5 different resistors. Looking at this, I kind of have to make decisions, just like we did for capacitors, about whether certain things are in series or parallel. Um, as you get a little bit better at viewing these circuits, certain types of visual cues kind of stand out. For instance, the fact that there's a box right here kind of tells me that something's going on with parallel because we have a pathway that's splitting. Similarly, the fact that this one is all kind of on its own tells me that it's probably going to get incorporated through series, and then same thing with the box idea down here. Now in this case, if I look at R3, for example, and I'm following a pathway around this circuit, I can see that it's in series with different resistors, but the problem is that R3 is kind of in series with R4, but it's also kind of in series with R5. And R4 and R5 are not in series together, and so I can't really do anything with series right there. What I can do, though, is look at kind of these boxes. And if I look at R1 and R2, for example, I can see that they are in fact parallel because they connect on this side and they're directly connected to one another on the other side. Now, I cannot call them parallel with R4 and R5 because, again, if I'm looking at this side of the circuit, I can't get to R4 and R5 without passing through the battery. And similarly, on the right side of the circuit, even though they're shared here, I can't get to R4 or R5 without going through R3. So they're not all 4 in parallel, even though they're kind of lined up visually like this. But I can say that R1 and R2 are parallel. And so I'm going to go ahead and combine those. And just as we did before, I'm going to say that this is parallel. And I'm going to mark that it's R1 and R2 that I am combining. And I'm going to redraw this. 12 volts and 1 combined resistor now at the top. Still have R3 off by itself, and I still have now R4 and R5 down here at the bottom. It's okay to draw this a little bit smaller just because the important part is just staying organized with what it is that I'm doing. So I'm going to call this R1, 2. And for resistors that are in parallel, we have to find the equivalent resistance, and the equation for parallel is 1 over R1 plus 1 over R2, extending, however far, however many resistors we have in parallel. In this case, though, I just do 1 over the quantity 1 over 6 plus 1 over 4, and when I do that, I get a resistance of 2.4 ohms. So I get 2.4 ohms for this combined resistor. R3 is still 4. R4 is still 6. And R5 down here is still 9. Looking at this again, I have a couple ways I can go with this. If I want to consolidate this a little bit further, and because ultimately I want to get down to 1 resistor, looking at this I can see R4 and R5 are parallel. Now, in truth, R1, 2, this combined one up here, and R3 are definitely in series. And this is where kind of experience helps you out, because I could combine these in series, but the problem is once I combine these two down here, R4 and R5, they're going to actually be part of that series too. And so if I combine these in series and then I do the R4, R5, I'm going to have to do another series combination on top of that. And so instead, what I'm going to do is I'm going to go ahead and just take care of that parallel right here. So this is going to be another parallel combination of R4 and R5. And I'm going to redraw it. There's my battery, 12 volts. There's my combined R1, R2, R3, and now my newly combined R4 and R5. Okay, so this will be R4, 5, R3, and then my combined 1, 2. When I do, I want to plug in these values, so I have 2.4 ohms, I have 4 ohms for R3, and now my combined R4, 5 is going to be doing the same equation that we did up here, except now when I plug in my values, I'm going to do 1 over the quantity 1 over R4, which was 6, plus 1 over R5, which was 9. And when I do that, I get 3.6. 3.6 ohms. Okay. Now, as I had previously mentioned, I can see that I do in fact have 3 resistors in series, and so I'm just going to jump right in and consolidate these in one final step, which should get us down to 1 resistor. So this is series. It's R1, 2 plus R3 plus combined R4, R5. And that gives me 1 battery, 12 volts, and 1 resistor. To find this one, because they're in series, I actually just add the resistance values. The reason for that is because any electron that leaves this battery is going to have to go through all 3 of these resistors, and therefore it's going to experience kind of that slowing effect, the resistance of all 3. And so I add those up. So 2.4 plus 4 plus 3.6 gives me 10 ohms. And now that I have that, I have R equals 10 ohms. I know that my current and voltage can be found because I have 12 volts as the voltage across this resistor. I know that because any electron that goes through this resistor will effectively have gone to the other side of the battery, which is the full 12 volts. So once I have that 12 volts, I have 10 ohms, and I can find then my I value, which is 12 divided by 10, which will give me 1.2. At this point, now I have 1.2 amps is my current through this, and I have 12 volts as the voltage across it, and now is where I can start going back to my previous drawings. And it's also why my previous drawings are so important. So in thinking about this, what I first have to remember is that I last combined 3 things that were in series, and any 3 or any number of resistors that are in series will have the same current. So it is going to be the current that I carry back with me. So the current here is 1.2 amps, and the current through this one is 1.2 amps, and the current here, 1.2 amps. This is important because, or rather, I know this because as electrons leave here, they only have one pathway to follow. You can't have electrons going really quickly, a high current through this one, and then a slow current here, and then a high current here. It just doesn't make sense. It's like cars down a highway. If there's only one lane and it's full of cars, they're all going to be going the same speed. You can't have some going faster than others. They'll pile up and bad things will happen. So at this point, I know the current through all 3 of these, and so I can find the voltages for each. And you'll notice it's getting a little messy with keeping things organized. I'm keeping resistance, current, and voltage together for each one of these. And then what I'm going to do is, as I solve these and I get down to the individual resistors, I can bring back my information to my original drawing. So for instance, if we start with R3, I know that V equals IR. And therefore, if I have a current of 1.2 and I have my resistance of 4, I know that the voltage across this one is 4.8 volts. And now R3 is really done, so I can bring that information back. I have 1.2 amps and I have 4.8 volts, and I'm done with R3. Finishing the other two, if I do 1.2 times 2.4, I get about 2.9 volts for this one. And if I do 1.2 amps times 3.6 ohms, I get about 4.3 volts. Just to check my work here, if I combine my voltages here, I get 4.3 across this one, I get 4.8 here, so that gives me 9.1, and then I add to that 2.9, and that adds up to 12. So far my numbers check out, and I can be reasonably confident that my answers so far are correct here, because it adds up to the 12 of the battery. Continuing back, the last thing I did was I combined R4 and R5 in parallel. Any resistors in parallel will have the same voltage, and so I carry back the voltage with me. So I have current 5, I have voltage 5, and same thing up here, my voltage for number 4. Um, they're both going to be the 4.3 right here, so I carry back my voltage 4.3 volts. And this is going to get interesting. I will write this. I'm going to write it over here. So current 4 and voltage 4. Voltage 4 is 4.3 volts. Okay, so now I can find my current. Again, I go back to the equation V equals IR. If I know that V is 4.3 and I know that my R in the case of R4 is 6, I do 4.3 divided by 6 and I get about 0.72, so 0.72 amps. If I look at I5, I know that V is 4.3. I divide that by 9 and I get about 0.48 amps. 0.48 amps of current. I can check this because the current that's coming in to this from the battery, as we saw back here, is a total of 1.2 amps. And if I have 0.72 going up this way and 0.48 going this way, when I add those two numbers together, I do get the 1.2 amps. So again, another way I can check my work as I go along. And at this point, we are actually done R4 and R5 as well. So I'm going to add in those numbers back on my original drawing, 7.72 amps and 4.3 volts and 0.48 amps and 4.3 volts. Only one last combination to cover, so I look at R12, and I want to think back here. I knew that the voltage on it was 2.9, so the voltage on 12 it's still 2.9. I'm just writing it here so I have it. When I look at these two, they were combined in parallel, and so it's the voltage again that I carry back with me to each of these. So 2.9 volts. 2.9 volts, and I just have to solve for current. So if I look at R1, 2.9 divided by 6 gives me 0.48. And numbers are working out similar to the other parallel circuit. So if I do 2.9 divided by 4, I end up with about 0.7. I actually end up with about 0.73 here. That's okay. If I add up those current values, I actually get 1.21 amps. Not a problem. As I've mentioned in other videos, when we're doing this and we're doing rounding and significant figures and things like that, we're bound to get numbers that don't match up 100%, but I get 1.2 amps through this when they're combined, and I get 1.21 here. It's not a big difference, and it's not something that I really need to worry about. If I was worried about it, I could still go through and I can check my voltages, because if we follow any one pathway through this circuit, my voltages will add up to 12 volts. And as we go through, if we go through this way, it's 4.3 plus 4.8 plus 2.9, that adds up to 12. If I go another way, it's still 4.3, it's still 4.8, it's still 2.9, and it still adds up to 12, no matter which pathway we take. And so because of that, I'm pretty confident that all of my numbers are correct, and I have solved for what the current running through each resistor is and what the voltage difference across each resistor is. And there we go. That's solving a little bit more complicated circuits in involving resistors.